Gnanam paramam dheyam. Knowledge is supreme.
So let us now look at the limitations of all these control strategies which we have seen. So we will start with the P controller. So limitations of these control actions. When we talk about only the P control, the main limitation is that we do not get offset free response. So always the response will have some offset. And there is one more thing which whenever you have a proportional controller, it results in proportional kick. When we have a servo control. So proportional kick, by proportional kick what I mean is whenever you have when you request certain response, let us say at certain time I requested a set point change. If we try to plot the response of the manipulated variable or the controller output, what you will notice that so the moment this step is applied, the controller will ask a rapid change in the manipulated variable and then alternate, and eventually it will reach whatever is the final value. So this initial jump, the moment the set point change is requested, is known as proportional kick. So that means it just kicks the response, it just asks the response or the manipulated variable to go to a new value almost instantaneously. Again, practically this is not possible and it will cause a little delay in terms of reaching the final steady state, but the idea is that it causes this abrupt change in the manipulated variable, and this proportional kick is proportional to the controller gain. So again it tells me that the higher the controller gain I go with, higher in terms of magnitude, the proportional kick will become bigger and bigger. So again that puts limit on the value of Kc I can go with, because we had seen that for a P controller, higher the controller gain, smaller is the offset. So we typically want to go with higher controller gain, but at the same time this proportional kick also increases, which puts a limit on practicability of operation, and again that kind of limits how much controller gain we can go with it. This higher value which is requested may be more than the maximum value, and in that case again that particular value may not be physically realizable. So that is the disadvantage or limitation of P control, is that it will always result in proportional kick when we have a set point change. Now as this is the limitation of the proportional action, this same kick will be present whenever you have even integral action or a PI controller or a PID controller as well. Now let us quickly look at how to compute this proportional kick. For that what we are interested in is finding out, so what we are interested in is u over y set. So when we change the set point, how does the controller output change, and this can be derived as GC over 1 plus GP, GC, GV and GM. So, the easy way to obtain these transfer functions is if we look at the closed loop transfer function block diagram. So, the way to get any of these transfer functions, we may be interested in the transfer function between u and y set, u and d, may be interested in how the manipulated variable behaves when we have a set point change or the disturbance occurs. So, in all these cases you do not need to go through the entire derivation every time. The easiest way to find out these transfer function is to trace the path from the input to the output. So, let us say if we are interested in finding this particular transfer function between y set and u, you just find out what is the direct path between y set and u. So, when we are going from y set to u, what we are seeing is there is only one transfer function in between. So, we call it, we put that here, and then the denominator depends on the denominator is always 1 plus all the transfer functions in the closed loop. So, the transfer functions in the closed loop are GP, GC, GV and GM. So, it will be GP, GC, GV and GM. Using the same logic, if we were interested in finding the transfer function between, let us say, US over DS, then the denominator remains the same because the closed loop is not changing. But for the numerator, now we have to go from D to U. So, the path it is going to take is this. So, let us go through all the transfer functions. So, you have GD, then you have GM, and then we have a negative sign because the effect gets inverted. So, you also have to carry that negative sign here, and then GC. So, that way you can always find the transfer function between any two variables within this closed loop system, and then when you try to find out whenever there is a step change in terms of y set, you will see that the response between u and y is a first order lead lag type of system, and that is what causes the initial value to abruptly change to a new value, and that difference gives you the proportional kick. Let us now look at the limitations of PI control. So, one limitation is that it increases order of system. So, it makes the system sluggish. Though this is not a very big disadvantage, the major limitation from PI, because partly it is covered because we have also added some numerator dynamics. So, effectively the system response can still be sped up. The major limitation of a PI control is what is known as integral wind up. And this is present because of the integral action. So, it will be present in PID also, because it is the product of having an integral action into the system. So, as integral action is present in PID control as well, this integral wind up may also occur during PID control as well. So, let us look at what is a integral wind up. So, for that let me consider a simple example of a surge tank. So, let us consider a surge tank where the inlet is coming at the flow rate of 0.1 meter cube per second, for example. The area is 1 meter square and the level is currently 0.5 meter. Outlet there is a valve whose transfer function is, let us say, given by this. So, the maximum flow this particular control valve can take is 0.2 meter cube per second. So, at any time it can take almost twice the inlet amount of flow. So, by that, at steady state, when inlet equal to outlet, the flow rate will be 0.1. So, the valve will be 50% open. We are considering a linear valve, so that the flow goes from 0 to 0.2. So, at 0.1 it will be around 50% open, and we have installed the PID, we have installed the PI control on this. So, we measure the level, so level indication, and then it goes to the comparator, and from that comparator it goes to the level controller, and the level controller will give a signal to the valve opening, and accordingly the valve will open or close depending on whether the height is at the steady state or not. And we are interested in moving the level from 0.5 meters to 0.75 meters. So, that is our objective. So, it is a servo problem, and the values of controller parameters we are going to use is Kc equal to 5, and we will use integral time constant of 1. So, let us see what happens. So, let us try to calculate manually how does this particular control system is going to operate. So, we will also assume that the controller frequency is 1 second. So, whenever the controller takes any action, that action will remain there for 1 second, and then after every second the controller will take an action depending on the feedback interaction with the system. So, for this particular system, let us tabulate how the system will respond. So, we have time, we will monitor how the height is going to change, correspondingly what is the error, what is the value of controller output we are going to get, and accordingly what will be the outlet flow rate. So, let us start with time t equal to 0, the height is 0.5, and as we have requested the set point to be changed to 0.75, it causes the error to be of positive 0.25, and accordingly the controller will take action. The initial value is 0.5, it is going to be a direct acting controller. So, the controller gain has to be negative. So, it will be minus 5 times error, which is 0.25, which comes out to be minus 0.75. So, it says that the controller output has to be minus 0.75, but the valve can only have opening between 0 and 1. So, practically it is equal to 0. That means valve completely gets closed and the outlet flow rate becomes 0. So, suddenly from 0.1 meter cube per second, the outlet flow rate has suddenly stopped to 0. As the outlet is 0 and the inlet is 0.1 meter cube per second, the net influx of material into this tank is going to be 0.1 meter cube every second, area is 1 meter square. So, the height is going to change at the rate of 0.1 meter per second. So, in 1 second the height will increase by 0.1. So, the height will be at the end of point 1, at the end of time 1, the height would have reached value of 0.6. The error is now better, the error has become 0.15, and the output will be now 0.5 minus 5 times 0.15 plus integral of error. So, the integral of these two errors will have 0.25 plus 0.15 over 2, which comes out to be minus 1.25. So, again this is less than 0. So, practically the valve is still closed. So, outlet is still 0. We reach the time 2, the level by then would have reached 0.7, the error becomes 0.05. When you calculate the output for this, it comes out to be minus 1.25 again. So, again the valve remains closed, and then at the next time instant the value of level, the level is going to cross the set point. So, our set point was here, so we have already crossed the set point. The error will now become minus 0.05, and at that moment if you were the person who is controlling this process, ideally you would have wanted to have the outlet flow to be greater than the inlet flow, so that the level will eventually try to come down from this point at. However, what you will see that the controller output in this case is again minus 0.75. So, the valve still remains closed. So, now you should be able to see the problem. So, you are seeing that the set point has gone, the value of the controller output has gone beyond the set point, but still the control valve is closed. So, that is the problem, because we are spending too much of effort on the integral action. So, all this is happening because of the integral action. The derivative action has already helped you or told you that the output, the controller output has to increase, but the integral action is kind of dominating the proportional action, and the valve still remains closed. If you try to continue with these calculations, what you would see that the level at the end of 5 seconds would reach 0.95, and then will be the time when the level, when the outlet flow rate would eventually be 0.2 and the level would start to drop. So, the level will reach a value of 95%. So, the valve tank will be almost close to full level, even though the set point was 75. So, the offset the overshoot was almost 0.2, and this whole thing is happening because you are penalizing the integral action. So, all these high negative numbers we are getting, even for the error which is positive, which is correct, and negative error is penalizing the controller, even though it is doing maximum it can. So, even though you are asking it to become highly negative, or you are actually asking the outlet flow rate to go down, it has already gone down to the minimum value. So, it can no longer go further down, but still you are penalizing on that poor performance of the controller. So, that is not correct. So, that is the reason why you get such a high offset from the current value, and this particular thing is happening because the control valve is saturated. So, in that case there is no point on accumulating the error, and this is the thing which is causing this high overshoot. This particular phenomena is known as integral wind up. So, it will be present whether you have a PI controller or a PID controller. Whenever the control wall gets saturated, there is no point in keep on adding or having the integral action, because it is unnecessarily going to accumulate all these errors as a history, and then whenever the response or the wall becomes in order for the wall to become in control, a lot of undoing has to be done for all these accumulated errors. So, this is known as the integral has wound up. So, now it has to unwind before it starts moving in the correct direction. So, that is the limitation of integral controller, that it can cause this kind of integral wind up, which results in very high overshoot values. The way it can be corrected is by having anti-reset type of action. That is known as anti-reset wind up strategy. So, one of the strategy can be to turn off integrator when control wall saturates. So, it makes sense that as the control wall has already saturated, as the control valve is saturated, it can no longer move the system, it cannot do anything better than that. So, there is no point in keep on penalizing for the history or the bad performance during that phase. So, if you do that for the same example, the maximum level to which it goes suddenly reduces to 0.775. So, overshoot is drastically reduced and the control wall also opens when level was 0.7. So, before the set point, so that it starts taking the corrective action and does not, because of that the level does not go too far beyond the set point. So, that is the limitation of integral action, that in certain cases it may result in integral wind up, and the controllers whenever you have integral action as a part of PI controller or PID control, you have to have some sort of anti-reset wind up strategy. One of those strategies is just turn off the integrator whenever the controller saturates. So, let us now complete this analysis with the limitation of PID controller. And so, here he will exclusively look at the limitations coming because of the derivative action. So, as we are using PID controller, it is anyways going to have the limitation of P controller, which was the proportional kick, the limitation of integral action, which causes reset wind up, integral wind up. So, both these things are already present when you have a PID controller. In addition to that, a PID controller has a limitation when you have noisy input or noisy data. So, let us look at an example that this is your set point and the output response in a typical real life plant would be something like this. So, it will be moving around this set point. It will never be exactly equal to set point, or it will not exactly remain at the set point, because there are a lot of disturbances in terms of signal transmission, or also some small disturbances which are happening in the plant at a very high rate. So, the actual response may not exactly lie as a flat line, but it will keep on having certain vibrations or oscillations around this set point. So, this is the Y is our output. So, if this is the plant which is given to you, would you take any action to remove these small wriggles and then make it Y as equal to Y set? So, in reality you would not want your controller to take any action because of this. However, if you magnify this particular portion, what is happening is the system is continuously moving up and down from the set point. So, this is just a magnified view of this. So, what you are going to see is in general the proportional controller is not going to take any action here, because the magnitude of error is very small. So, error is always going to be between these values. So, the P controller will not take any action for that. If you look at this integral of the error, those are also very small. So, the I control, or let us say Pi control, the integral action again will not take any action. But if you look at the derivative action, you will see that here the derivative is positive, suddenly the derivative is negative. So, the derivative value can be much larger than the actual value of the error, and in that case what is going to happen is the derivative action will actually try to react, or will try to take action to eliminate these kind of small fluctuations in the output, which are actually not required. So, in that case what is going to happen is, because this error is changing direction, the derivative actions will have very significant amount of contribution will come from the derivative action, and if the tau d is not selected properly, or the tau d has a significant value, then the controller will try to get rid of these fluctuations, and as these are natural fluctuations where nothing can be done, in this case the manipulated input or the controller output is very much closer to whatever is the desired value, but because the derivative action is trying to react to these fluctuations, it is going to change. So, the PID controller will cause you to move away from this desired value, and because of that the closed loop response may become unstable, or it will start oscillating at a much higher amplitude. So, that is a very common problem in real plants, that whenever you have a derivative action and it is significant, it is going to react to this noisy measurements, noisy data, and because of that it is going to cause bigger oscillations into the process rather than not having any derivative action. So, the derivative action will always try to react to this noisy data, and to eliminate that you typically have filters. So, noise filters are required, but still the data can never be smooth data in the real plant, and the PID controller will still try to react to it if the derivative action is not correct. So, that is a very major limitation of a derivative action, which significantly limits the implementation of a PID controller. So, unless required, the derivative action is typically never used in a real plant. So, that kind of sums up about the limitations of these three types of controllers. So, let me just show you some sample responses for a simple liquid surge tank, and how does a PI and PID controller responses look like, and for a regulatory problem, in this case we will have a same set point about the effect of input disturbance, and then we will also see what is the effect of controller parameter. So, let us start with a simple P controller, and you will see that as you start increasing the gain of in all the responses, you can see that there is always an offset, the level is never equal to the 50%, which is the set point, and as you keep on increasing the controller gain, your response will start moving towards the desired value. So, the offset keeps on reducing. So, as you have higher values of Kc, lower will be the offset, and also response will be faster, even though in this simple example the speed of response is not that clear, but in general it will be faster as you increase the gain. Now, let us say on top of that you also add an integral action. So, here are the responses when for the same system, same disturbance scenario, you add integral controller. So, you can see that as you have a very high value of integral time constant, let us say the tau I equal to 10, In that case, what you have is the integral action contribution, the weightage is less compared to the proportional action, and the response is very slow. It is almost as like a peak simple integral controller with very so what you get is a very slow response to the final steady state. As you keep on adding or increasing the contribution of integral action by reducing tau I, you will see that the response becomes faster and faster. But in all the cases what you are seeing is that there is an offset free response. All the responses go to the set point value. Smaller the value of tau I, faster will be the response, but at the same time it comes up with a disadvantage that the response becomes oscillatory. And then we look at the addition of a derivative action. So what this derivative action is going to do is, it is going to bring down that peak value. So it is going to reduce the overshoot by having an increased value of derivative action. We are going to get smaller overshoots. So in summary, if you look at the comparison of all these three actions, the proportional controller gives you a fast response, non-oscillatory response, but the offset is not equal to 0. When you add integral action, the response becomes oscillatory, it reaches the offset becomes 0, but there is also some overshoot, and then when you add a sufficient amount of derivative action, even that overshoot can be reduced. So in summary, what you can see is that the P controller is the simplest controller to implement. It is very fast in terms of taking action, but the disadvantage is that it cannot guarantee you offset free response. In order to get rid of that offset, you add integral action, so it gives you offset free response, but then it increases the order of the system, and so it slows down the system response. It also introduces oscillations into your process. The addition of derivative action, so overall PID controller gives you offset free response as well as relatively faster response, smaller overshoot, but then one of the disadvantages is that it will react to noisy data. And other thing is, now you have to coordinate three actions. So when you have a PID controller, you have to look at what is the contribution of integral action, contribution of derivative action, and contribution of integral action. So all these three have to be properly, the weights of these three actions have to be properly set in order for that controller to give you these desired outputs. If one of those overweighs the other two, then these advantages would not be realized in practice. So we will see what is the way or what is the best practice in terms of going forward with these values. That will be the part of controller tuning. So in general, to summarize this, if we have to really design a controller for any system, which is going to be the topic of next the week after next, what you do is you start with a P controller. So the simplest thing, whenever you have to implement a controller, you start with the simplest controller like a P controller. If and it is going to give you fast response, but it will be with offset. So if offset is not desirable, if you want the process to always reach its set point value, then you will go for a PI control. If the addition of integral action is going to slow down the response, then you will also add a little bit of derivative action and you will go with a PID controller. In general, if you visit any chemical industry, you will see that most of the controllers, wherever offset is undesired, then you will all see that a PI controller is used rather than a PID. The reason being, the derivative action, obviously it reacts to that noisy data which is part and parcel of a real plant data, and also the other thing is having properly tuning the relation, the weightage of these three actions is really a tricky job. So that is why most of the times we stop at a PI control, and unless the system demands that a derivative action has to be there, you will not go with a PID controller. And then lastly, what is the best value of these controller parameters like Kc, tau I and tau d, that problem is known as a controller tuning problem. And as I said earlier, will be that where we talk about what is how these values of Kc, tau I and tau d would be selected, so that you get these advantages in place, and we kind of limit the limitations of these control actions. So we will stop here at this point, and in the next week we will look at one of the products of this having a controller on the system, that is known as a stability analysis. we'll see what do you mean by a stable system or unstable systems, and we'll look at what is the implication of having a controller on top of a system. So we'll stop here. Thank you.